Hey everyone, welcome to Ophthalmic Optics. We have a ton of material to go through. We're going to organize, simplify, and dominate. Let's get started. So in this video, we're going to talk about several topics. We're going to talk about indirect ophthalmoscopy, lensometry, hand neutralization, and then radioscope. So let's dive into the text. So if you guys look in your text, you'll see ophthalmoscopy. We all know this is how we can view the retina. If you look in that box in the middle of your text, you're going to see indirect ophthalmoscope, and you can remember that's kind of like BIO, so binocular indirect ophthalmoscopy. And there's just some characteristics that you want to put a highlighter box around that, or highlighter star if you want to there. Larger field of view, larger depth of focus, smaller magnification, and we all know with BIO there's going to be an inverted image, all right? So put a highlighter box around that. We're going to dive more into that topic whenever we get to the live lecture. So now let's go into lensometry. I'm going to take this to the whiteboard to help us understand that topic a little more thoroughly. So you already have this picture in your text, so you don't necessarily have to draw everything out that we're going to be doing here, but I wanted to kind of go through and talk about, like, break down a lensometer, and so you kind of understand like what's going on with lensometry, because it will help us be able to address an optics question that comes up that we don't think about in clinic, but makes for a good optics question as we're going forward. So whenever you guys look in here, so you'll see I drew in a tube because the picture that I have, I kind of drew in a tube here because whenever you think about doing lensometry, like the old manual lensometers, right? There's this big long tube. You have the dial here at the back, right, that you spin to be able to locate the axis of your line, to make that line images clear, right? So you have a standard lens right here, right? And then here's going to be your patient's lens or the test lens. Right? So here's the patient's lens here, right? And if you think about it, there's really kind of like this little platform, right, that you have that the actual prescription sits on, right? And if you were to take and actually unscrew or snap off that platform, you would see that there's this, you're going to see that there's this big lens, right? Right here, it's kind of a flat lens that sits in there, and that's just a really high plus powered lens to help you be able to neutralize a patient's prescription. That's going to be called the standard lens. I just put an S up here. You'll see in your text you guys already have standard lens. So then we have a telescope, and then we have our eye that we're looking through here. So a little black box right there between the patient's lens and your eye is going to be your telescope. So first thing whenever we're doing lensometry, always what do? We clear up the eyepiece, right, to make sure that we're not over accommodating. Then once we go from there, we put the patient's prescription in there. Now all of our line images that we're viewing are going to be blurry, right? And so what do we do next? Well, next we take our dial, right? We've got that big circular dial on the side of the lensometer, and we move that thing in and out, right, to neutralize the patient's prescription. Now, whenever we move that big rotating drum, right, to the red or to the black, what are we actually doing? Well, we're actually moving this target inside this long tube, right? And what is our target? Well, our target is just those up and down lines, right? It looks like a tic-tac-toe pattern, and we'll talk about that here in just a minute as we continue on with this topic. So the key point here that I want to go over with you guys is that there is a mathematical way to be able to figure out what is the patient's prescription based only on how much you move the target distance-wise and the power of this standard lens, right? And so we're going to talk about that in a second. Before we get there, we need to understand one thing here. So if we move the target closer towards us, right? So I want you guys on your picture here in your text, draw a little arrow right underneath that target towards the standard lens, right? And if we take that target and move it closer towards us, right, that's going to be a plus patient lens. Okay, so that means that this patient's lens here is going to be a plus lens. We're going to have to move that target closer towards the standard lens, right? So that's going to, and then you could also write in like move target forward. Right? So if you hear a problem, say you move the target forward to get neutrality, right? Or to neutralize the image, right? Then that means that the patient has a plus lens. If you have to move the target away from you, right, to make those lines clear, that's going to be a minus lens. Right? And that's going to be move the target away. Okay? So you're going to move the target away. All right? So key point there, if you move the target away, it's going to be a minus lens. Move the target closer towards you, it's going to be a plus lens. Now, do you guys really care about that much whenever you're in clinic? Absolutely not. We're going to talk about clinically neutralizing prescriptions here in just a second, but this is kind of the optics behind this. So if you guys look in your text, right, down here below, you're going to see an equation, right? The equation is x equals f, fancy F squared, FV, right? That's going to be the lensometry equation, right? And so this is the mathematical way to be able to figure out what is the patient's prescription, right? Their back vertex power, right? Based only on how much you move the target and what is the standard lens power, okay? So this X right here is how much you move the target. So right here, I want you guys to put an X right above that little arrow so you guys remember that's going to be what we're talking about is X is going to be the distance you move the target, all right? And then the little f squared is going to be the focal length of your standard lens. So it's not that the standard lens may be a plus 20 lens, you'd have to actually do 1 over 20 to get its focal length, and that's what you're going to square to be able to use this calculation. So if you guys look in the text, you guys will see that right underneath that you can highlight that. X is the distance the target is moved, F is the focal length of the standard lens, and FV is going to be the back vertex power. Now, last really important point. Look at that equation. How are you going to get a negative back vertex power? Right? How do you get a negative sign for your back vertex power? You're not going to get it from the focal length because that's going to be obviously a plus number because it's going to be squared. It's going to be your x is going to have to be negative. So the last key point here on this equation is that if you move the lens away from you, that represents a minus x value. If you move the lens closer towards you, that's going to represent a positive x value. All right? Not something that we're going to do in clinic, but it makes for good optics questions. So let's clear the board and let's work example 5.1. So example 5.1 says, let's say we are using a plus 25 standard lens, right? To achieve appropriate focus, we must move the target 2.0 millimeters forward, right? That's keyword, forward, right? You want to circle that whenever you're looking at the example. What is the back vertex power of the lens being tested? So I want you guys pause the video, take a second, work it out, and then we'll work it together on the smartboard. So look at our solution for example 5.1. One thing I want to point out about this equation for lensometry is that both x, right, the distance that you move the target, and little f, which is that focal length of the standard lens, both those need to be in meters. Okay, so key point there is that both need to be in meters, right? So make sure you convert the meters. So we did that here, right? Both of them converted into meters, okay? And then now what we're going to do is just going to plug them into the equation. We're going to solve for FV, so we're going to divide by our focal length of the standard lens squared. We're going to put our x on top. Remember, it's a positive x, right? And that's because the lens is going to be moved forward, right? So that's a key point. If the target is moved forward, the target is moved forward, you're going to have a positive value for your x. If the target is moved away from you, remember that's going to be a negative value for your x. So whenever you plug that out, you're going to get a final answer of plus 1.25 diopters as your answer for the back vertex. So once again, this is not going to be something you're going to do in clinic, but it makes for a good optics question. There's going to be more flashcards on that you're going to be able to go through as well. So last thing I want to hit on here with lensometry is I want to talk about just how you look at how prism influences your target, how you calculate prism with lensometry. So let's clear the whiteboard and let's talk about that. So now we're going to talk about some generic rules for verifying prism with the lensometer, right? You've got this nice box there in your text. You guys will see this all the way around. Just put like kind of a star around that. It's going to be a key point we want to talk about. So remember, whenever you're looking through a lensometer, there's a couple things you're going to see. One of them is going to be like a tic-tac-toe pattern, right? And that's going to be your vertical and horizontal lines, 3 of them being wider, 3 of them being thinner. And so you're going to see that. A lot of times that's going to be green. It could also be white depending on your lensometer. The other thing you're going to see whenever you look in the lensometer is you're going to see your bullseye, right? So you're going to see 3 circles, right? So there's your bullseye pattern that we're going to see. So what we need to talk about is how are we going to verify prism by what we see in the lensometer, right? And here's some generic rules. So the key point, and we're going to talk more about prism today whenever we get into the videos about prisms here with ophthalmic optics, is that light deviates towards the base, right? So we're going to talk about this again. Remember, light deviates towards the base. So what we're viewing in this tic-tac-toe pattern is the light coming from the target, right? And so we're actually viewing how much that light is going to be deviated. So let's look at some of these bullet points. I want to hit on the third one down here. It says, if the center of the crosshairs falls above center of the bullseye, right, what kind of prism is going to be induced? So let's draw that picture out. So if we have our bullseye here, right, our tic-tac-toe pattern, right, is going to look something like this. right? So here's our tic-tac-toe pattern, right? It's going to be above center, right? So if it's above center, that's going to be base up prism, okay? So if we draw out the picture, like if we think about their lens actually looking at the lens like we're looking into the lensometer, right? If they have base up prism, right, it would look something like this, right? Base up prism. And so whenever we think about the targets here inside the lensometer that we're looking at, the key take-home message for you, and I think what's going to unlock this whole entire box, is just that the crosshairs deviate towards the base prism, right? So in terms of verifying prism, right, the crosshairs, right, deviate towards the base. Right? So here our crosshairs have been deviated superiorly. That means that we have base up prism. If our crosshairs are moved down here inferiorly, right, that means we're going to have base down prism, right? So I think that's going to be hopefully an easy way to be able to go through that, go through those examples and kind of understand that. I think it'll hopefully help unlock that concept, which, to be honest with you, is kind of a difficult concept that I've seen working with students throughout the years. So like I said, the take-home message is your crosshairs deviate towards the base. All right, let's clear the whiteboard and let's work one more example. So let's dive into example 5.2. When using lensometer, the sphere power is found to be -3 diopters and the axis is 125. The power wheel is then rotated in the minus direction until reaching a power of -4 diopters, at which point the cylinder lenses become clear. What is the power of the lens? So go ahead and take a second, pause the video, work out the problem, and then we'll work it together here on the whiteboard. Whenever I work these examples in lensometry where they give me a word problem where, we're used to doing lensometry and just doing it and kind of not even thinking about it and just neutralizing a patient's prescription. But in a word problem, it can be a little more challenging. So I know on the surface this seems like a really easy example, and the truth be told, it is. It's one that we want to be able to dominate if it comes up on boards. But I also want to make sure you guys don't skip over this, just like lens transposition, because it's going to be really important to dominate, these easier type of questions. So for me, I'm always going to put things on a power cross. So instead we had -3 at axis 125. We rotate the dial 90 degrees, and now we get a -4, right, as our absolute power. So when we're writing this in -sil prescription form, we're going to have -3, -1, axis 125. All right, guys, you're doing great. Let's clear off the whiteboard and let's keep on going to our next topic. So let's talk about hand neutralization. So whenever we look at hand neutralization, you kind of think about, okay, when are we going to use hand neutralization? Well, the reality is in clinic, not that much, right? I mean, you maybe a situation where, you're heading home from clinic and you've got your white coat on for some reason on the subway, right? And you're just asking people to ask you, like, what do you do? And they say, oh, I'm an optometry student. And they go, oh, yeah, great. I'm wearing glasses, but I'm really confused on whether I'm nearsighted or farsighted. So can you help me out with that? And you don't want to ask them all these questions, everything there. You just want to go, okay, and they hand you the glasses. Like, can you just tell from my glasses? And you go, huh, yes, I can. It's called hand neutralization, right? Because what you do is you look at an object, right? Close one eye and then look at, guys, I'm looking at the camera, right? I'm looking at the camera and I'm watching, okay, is the camera moving with my motion of my lens or against the motion of my lens? And that'll tell you whether you have a myopic or a hyperopic prescription, right? So what's the key take-home message for you is to remember which one's which, right? So if we're moving the lens and we're watching some object or like a wall, like the line on a wall or a window, anything like that, right? And the image goes with our motion of the lens, that's going to be what type of lens? Yeah, it's exactly right. It's going to be a minus lens, right? So let's highlight that in the text, right? So look in your text, minus lens is going to be motion, is going to be with motion. A plus lens is going to have motion. It's going to be against motion whenever you're doing hand neutralization. Awesome job, guys. Let's keep on going. Let's finish up this section by talking about the radioscope, right? So what's the radioscope going to be used for? Yeah, it's exactly right. It's going to give us the base curve, right, of a GP contact lens, right? So you want to highlight that in the text, right? So it measures the base curve or the radius of curvature of a GP contact lens. Now, how do we do this? You guys remember doing this in lab? Maybe you guys have done this in lab. Maybe you haven't at this point in time. Whenever you guys get there, you'll be like, oh yeah, okay, now I know what Ryan was kind of talking about. So remember with the radioscope, you're going to put the base curve, the contact lens in. Remember, we're looking at the back surface of the GP contact lens, right? Because that's where the base curve for a GP contact lens is in the back surface, right? Well, we're going to look at the contact lens. Remember, whenever we look through the little eyepiece, you're going to have a dial in there, and you're going to notice there's going to be going to be several clear images, right? There's going to be 2 clear images and then like a filament right in the middle, right? And so what's going to happen is that the key behind radioscope is that you're going to have one clear image, right? You're going to have the filament and then another clear image, and there's actually a scale on the radioscope that tells you the distance between those 2 clear images, right? So look in your text. The first image is going to be the location of the surface of the lens, right? So the first clear image is the image, the reflection of the image coming from the surface of the lens, right? Now the second one, look at the second point there, right? That's going to be located at the center of curvature for that GP contact lens, right? So one clear image is going to be the surface of the contact lens. The other clear image is going to be the radius, the center of curvature for that GP contact lens, right? And the key take-home message for you is in the box right below, right? And that the distance between those 2, right, is going to be your radius of curvature, right? So a lot of times we'll zero out the radioscope. So whenever we see the first image clear, we'll put a 0 mark there. And then we can rotate the dial and whatever number we come to, whether it's 7.1, 6.8, whatever millimeter number that is, that's going to tell us our base curve radius, right? The other thing that could be done is the question could say something like, okay, you get one clear image at 2, right? And the other clear image is at 8.3. Right? What is the base curve of your contact lens? Well, you would just subtract those 2, and the difference between those 2 would be 6.3, and that would be your base curve for that GP contact lens. All right? Great job, guys. Go dominate the quiz. We'll see you on the next section.